well, do that again. So we know that they're not spin liquids, right? We know they order magnetically into the zigzag pattern for the sodium, and for the alpha lithium, some indications of spiral order. Again, there's no definite statement on that just yet. So what else do we know about this order? Well, you might think that if we see this thing order, we might have gotten the spin liquid physics completely.
About K1, K2 model, apparently it's kind of new, interesting quantum/classical model, and the reason we studied this model was motivated by experimentalists. So let me first start by acknowledging my collaborators. So this work, which I'm going to talk about, is mostly done with Ioannis Rusha-Hatzakis, who is now in University of Minnesota, and Craig Price, who is in Penn State, and some previous results were obtained with Yuri Suzov, who is my PhD student, and with Peter Wolfe. And I also acknowledge collaboration with FRG guys, Stefan Rachel, Johannes Reuter, and Ronnie Tamari, who did the FRG study of this K1, K2 model. So here is the outline of my talk. So I will start with motivations why we decided to study this model, and I will advocate also the importance of second neighbor Kitaev interaction to resolve at least most of the puzzles connected to sodium iridate. I heard a lot about this compound already. And then I will present and discuss this K1, K2 model. So K1 is Kitaev interaction on nearest neighbor, and K2 is Kitaev interaction on second neighbor. And then I will discuss both classical and quantum phase diagram. And I will show that this model actually has completely different quantum and thermal speed fluctuations. And basically, most of the results which I'm going to present today is in the preprints, and some finite temperature properties are in preparation, so we are going to submit it. Okay, so I don't think that I need to go to motivation. So once again, it was the work by George and Guignat, who showed that in this family of iridates, honeycomb iridates, it can be very large Kitaev interactions which come from this interplay between super exchange arising through this 90 degrees hopping. And what was also important that in these compounds, Heisenberg interaction is there because 5d orbitals of iridium atoms are rather extended. And I think the main motivation for many experimentalists was that the spin liquid phase is in fact quite stable with respect to Heisenberg perturbation, and therefore it was, and maybe still, a big hope to see spin liquids in this compound. And basically in this original model, it was a part of spin liquid phase. It was two magnetic phases, simple two-sublattice antiferromagnet, in the state and small Kitaev interaction, and the stripy phase. And when people start doing experiments, especially in the sodium iridate, then they found something else. I don't need to repeat many things what just said by Radu Koldea, but let me tell what were the questions for myself, what I could not understand in this compound. So first of all, from quantum chemistry results, it was shown that Kitaev interaction is indeed the dominating interaction. It's ferromagnetic one. So basically, it fits to the description of this Kitaev-Heisenberg model. And if you just take these values and plug it, you should get spin liquid. But it's not in the spin liquid state. Both sodium iridate and lithium iridate, and now there is another compound, ruthenium chloride, they all order at rather low temperature. So this is question number one. why sodium iridate order? So, second question is why Curie-wise temperature is large and antiferromagnetic if we see that the dominant interaction is ferromagnetic. So that was question number 2. So basically the Curie-wise temperature which was obtained for sodium iridate was minus 125 Kelvin. So this we should understand too, I think. The third question was why it ordered to zigzag phase, while in the original model this phase was not present. And basically zigzag phase, you have 2 bonds, you have 2 ferromagnetic bonds and 1 antiferromagnetic bond, and you can have zigzags running in 3 different directions. And basically it was a suggestion first coming from Itamar and also from the paper of Rado's group, that it should be further neighbor interaction to explain zigzag. Question number 4 actually comes from very recent work by GEDC group, and we heard about this yesterday. So it's basically that the order parameter, the seams point in the phase diagonals. While if you do some order by disorder for nearest neighbor Kitaev Heisenberg model, then you see that both quantum and thermal fluctuations choose cubic direction. And then if you add more terms, and we heard about this by Kingyat yesterday, that in principle you can do some fine-tuning and get this phase diagonal direction. But we were thinking maybe there is something else behind this suggestion. So basically I want to point that the K2 interaction, the exact interaction on the second neighbors basically helps to resolve all these 4 questions. So what we did with Yuri and with Peter, basically we took the time-bounded parameters provided by Roger Valenti group, so it's Katerina Peresova, Igor Martin, other people in this paper, and they provide the Hawking time-bounded parameters for both nearest neighbor and second neighbor. And what we saw that actually the second neighbor coming through a complicated path, so this path actually involves, so it goes from iridium to oxygen, then to sodium, and then to oxygen, and then to iridium. So it's a rather complicated path which connects second neighbors. Basically, if you do the strong coupling expansion and you derive your super exchange Hamiltonian for second neighbors, then you first of all see that there are 4 paths which all add up. They basically give you the same contribution, and then you get that in the second neighbor you have the same type of Kitaev interaction as for the first neighbor. So it's basically, if it's kind of Z-bonds here, so if you couple these iridium sites with these iridium sites, then you again couple YZ and ZX orbitals, like for the nearest neighbor through the oxygen, and yet then you get to the Kitaev interaction. So then what we did, we took some reasonable parameters which describe sodium iridate. It has some signal distortion, spin-orbit coupling 0.4 electron volt, Kunz coupling, Coulomb interaction, and then the Hawking parameters from this time-binding model, and that's the number which we got for nearest neighbor and second neighbor exchange. So basically what we got is that the second neighbor Kitaev interaction is antiferromagnetic and is rather large. So basically in this minimal model we suggest for sodium iridate we need 4 parameters. Of course we can also have more parameters, but this seems to be the essential parameters. We also compute gamma terms for sodium iridate, and for sodium iridate it's rather small interaction.